Tonight, we're going to look at a place that seems far away and quiet, but hides stories few people ever hear. Antarctica. You've probably seen it on maps or in photos of endless ice. Scientists study it often when they talk about climate and Earth's past. But here's what most people are never told. Beneath the ice and snow are clues that change how we understand this continent. When you begin to learn what has been found there, when you see what the cold has kept hidden for so long, it changes how you look at this frozen land. This is not just a blank white space at the bottom of the world. It is a place with secrets so deep that they challenge what we think we know about Earth's history. And by the end of this journey, you're going to understand why Antarctica matters so much and why so many lessons about it are rarely explained. Before we go any further, if you enjoy calm and deep stories like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it helps this work continue. Now, let's begin. Antarctica stretches across the southernmost part of the Earth, a vast and frozen landmass that holds more ice than any other place on the planet. It covers an area of nearly 14 million square kilometers, roughly 1.5 times the size of Europe, though much of it is hidden beneath thick sheets of ice. From a distance, the continent appears as a uniform expanse of white, a frozen ocean of snow and ice. But closer examination reveals a landscape sculpted by millennia of cold and wind. Its isolation is absolute. The continent lies far from any other landmass, surrounded by the Southern Ocean, which roars with storms and icebergs that break off from its glaciers. Human presence is rare, and life is limited to the edges of the ice and the waters beyond. The climate of Antarctica is unlike anywhere else. Temperatures at the coast can dip below -20 degrees Celsius during winter, while the interior can plunge to nearly -90 degrees, making it the coldest place on Earth. Winds sweep across the ice plains, sometimes reaching hurricane force, carrying snow in sharp, stinging sheets. The air is dry, almost sterile, and the sun, when it shines during the summer months, does little to warm the surface. The continent experiences extremes of light and dark, with months of continuous daylight in the summer and unbroken night in the winter. These cycles shape everything from the behavior of animals to the schedules of scientists who work there, and they create landscapes that shift in perception from glowing white to deep blue in the long shadows of winter. The ice sheets that dominate the continent are colossal. In some regions, the ice is over 4 kilometers thick, pressing down with a weight that has slowly shaped the underlying rock for millions of years. Antarctica holds around 90% of the world's fresh water, locked within its frozen layers, and if even a fraction were to melt, global sea levels would rise dramatically. Ice flows slowly, moving from the interior toward the edges where it meets the sea, forming massive ice shelves that extend for hundreds of kilometers. These ice shelves are dynamic and fragile, responding to subtle changes in temperature and ocean currents. The surface of the ice is rarely flat. It crests and dips in drifts and ridges, and in places snow and wind sculpt the ice into sharp, jagged formations called penitentes, which glint in the weak sunlight like frozen blades. Beneath the seemingly endless ice, the continent is not entirely uniform. Hidden valleys, mountain ranges, and subglacial lakes lie buried beneath kilometers of ice. These features have been discovered through satellite imaging and radar mapping, revealing a world that is both ancient and preserved, untouched by the warming or erosion that shapes other continents. Mountains rise under the ice, some reaching heights comparable to the Alps, their peaks sometimes piercing the surface as nunataks, isolated rocky islands that appear in the middle of ice fields. Lakes lie beneath the ice in liquid form, kept from freezing by the immense pressure above and by geothermal heat from the Earth's interior. The existence of these hidden features is a reminder that beneath the stark white exterior, Antarctica is a landscape of depth, history, and complexity. Coastal areas of Antarctica are different from the interior. The Antarctic Peninsula stretches towards South America, a jagged line of mountains and glaciers. This region is comparatively milder, with temperatures rising slightly above freezing during summer months. Ice cliffs tumble into the sea, creating calving events where massive blocks break off to form icebergs that drift into the Southern Ocean. These icebergs are sometimes enormous, stretching for kilometers and towering tens of meters above the water. The waters surrounding the continent are teeming with life during the warmer months, supporting colonies of penguins, seals, and a variety of seabirds. The nutrient-rich waters feed krill, the tiny crustaceans that form the foundation of a complex food web. Farther inland, life is nearly impossible, limited to microscopic organisms that survive in snow and ice. The physical isolation of Antarctica affects both the climate and the ecosystems. Storms gather strength over the Southern Ocean and batter the coast, while the high polar plateau remains largely undisturbed. Because of the thick ice and extreme conditions, human exploration is difficult and expensive, limiting interaction to scientific missions and research stations. Seasonal changes influence travel. Summer brings longer daylight hours and slightly milder conditions, allowing ships and aircraft to reach research bases. Winter isolates the continent completely, when darkness, cold, and blizzards prevent nearly all access. This remoteness has preserved the environment, making Antarctica one of the last places on Earth where ecosystems function with minimal human interference. Antarctica's ice is not static. Glaciers flow outward, slowly creeping toward the sea, moving ice that may be tens of thousands of years old. Snow accumulates at higher elevations, compressing into layers of ice that trap air bubbles, dust, and particles from the distant past. At lower elevations, warmer coastal conditions allow ice to melt in small areas, forming melt ponds and streams in summer months. These features, while small, indicate that even the coldest regions of the planet are in motion, responsive to both atmospheric conditions and internal dynamics. Scientists monitor these flows carefully, as changes in ice movement can have far-reaching consequences for global sea levels and climate patterns. The continent's light cycles are extreme. During summer, the sun does not set for months, painting the ice in shifting shades of white and blue, creating illusions of depth and texture. Shadows are soft and stretched, revealing subtle undulations in the ice surface. In winter, darkness dominates. The sun disappears for months, and the only light comes from the aurora australis, which casts shimmering ribbons of green and pink across the night sky. These light conditions affect not only human activity, but also animal behavior, as penguins and seals adjust their feeding and breeding cycles to the prolonged periods of light and dark. In addition to climate and light, the geography of Antarctica shapes its interaction with the world. Ice shelves act as barriers between the continent's interior and the ocean, influencing ocean currents and the movement of heat around the planet. The high altitude of the polar plateau, combined with cold temperatures, reduces evaporation and creates a desert-like environment, despite the presence of enormous ice sheets. Winds are channeled along mountain ranges and over ice plains, creating katabatic flows that descend at great speed, carrying snow and ice toward the edges. These winds, often exceeding 100 kilometers per hour, further sculpt the surface, eroding soft snow and forming hard-packed drifts that shift with the seasons. Antarctica's isolation is mirrored in its ecosystems. Life is concentrated along the coast, where ice meets ocean, while the interior remains nearly devoid of visible flora or fauna. Penguins gather in dense colonies, their calls echoing across ice-free rocky outcrops. Seals rest on floating ice or swim in icy waters, hunting for fish and krill. Microbial life exists in unexpected places, in the snow, beneath rocks, and in subglacial lakes. These organisms endure extreme cold, high ultraviolet radiation, and limited nutrients, surviving where few other forms of life can. Their adaptations provide insight into the limits of life on Earth and the potential for life in similar environments elsewhere in the solar system. The sheer scale of Antarctica leaves a lasting impression. It is both immense and fragile, a land that dominates the southern hemisphere, yet remains invisible to most of humanity. The continent's ice is a record of Earth's past, its climate and its ecosystems, preserved in frozen layers that have accumulated over millions of years. Its remoteness, extreme climate and isolation combine to create a world unlike any other, one where scientific discovery must contend with environmental extremes, and where the natural processes of ice, wind, and cold continue unabated. The vast whiteness, the silence, and the unbroken stretches of ice convey a sense of permanence, but also fragility, a reminder that even the most remote and inhospitable places are interconnected with the planet as a whole. Every detail of Antarctica's geography, from its icy interior to the jagged edges of its coast, tells a story of endurance and isolation. The land is sculpted by forces both visible and invisible, from the pressure of thick ice to the strength of polar winds. Mountains rise like frozen sentinels, ice shelves extend like floating platforms, and hidden valleys remain concealed beneath layers of snow and frost. The continent is a testament to the power of natural processes operating over geological timescales, a landscape preserved by cold and isolation. As researchers venture into this extreme environment, they encounter not only challenges to survival, but also a world that has remained largely untouched, offering a window into the history and ongoing processes of our planet. Even the air over Antarctica carries a sense of the continent's character. It is cold, crisp, and dry, often carrying fine particles of ice and snow that reflect sunlight in dazzling patterns. Clouds are rare over the plateau, but can form along the coast, bringing storms that sweep across the land. The silence of the interior is profound, broken only by the distant roar of the wind or the occasional crack of shifting ice. This isolation has preserved not only the land itself, but also the clarity of scientific observation, allowing researchers to monitor climate, ice dynamics, and ecosystems in conditions largely unaffected by human presence. The vastness and isolation of Antarctica make it a natural laboratory for understanding the planet. Its ice sheets, glaciers, winds, and extreme light cycles are all interconnected with global climate systems. By studying these features, scientists gain insight into past climate patterns, the behavior of ice under extreme conditions, and the ways in which isolated ecosystems function. Every measurement, observation, and expedition contributes to a growing understanding of how Antarctica operates, how it influences the rest of the world, and how fragile and dynamic this extreme environment truly is. Antarctica is at once a land of extremes and a place of subtle detail. Every ridge, every snowdrift, every ice formation tells a story of long-term forces and short-term changes. Its isolation has allowed it to remain largely unchanged by human activity, But the continent is not immune to global forces. Even in this remote place, shifts in temperature, ocean currents, and climate patterns are recorded in the ice, offering a window into a world that is both distant and intimately connected to life across the planet. It is a land of silence and movement, of permanence and change, and of stark beauty that is unmatched anywhere else on Earth. Beneath the immense white surface of Antarctica lies a hidden world, a landscape that has been preserved for millions of years under layers of ice. The ice may appear solid and unbroken, stretching endlessly in every direction, but below it, mountains rise, valleys sink, and lakes glimmer in isolation. These subglacial features are invisible to the naked eye, yet they shape the movement of ice above and hold clues to the planet's deep history. Scientists have only begun to understand this concealed realm through the use of radar, satellite imaging, and other remote sensing technologies that reveal its contours without direct observation. One of the most famous hidden lakes is Lake Vostok, buried beneath more than 4 kilometers of ice. It is roughly the size of Lake Ontario and has remained liquid despite the crushing pressure and freezing temperatures. The water in the lake has been isolated from the atmosphere for millions of years, forming a sealed ecosystem that might harbor microbial life unknown to science. Drilling into Vostok requires extreme precision and care, as contamination could destroy the delicate balance of this ancient environment. Similarly, Lake Whillans, though smaller, lies under nearly a kilometer of ice and has provided scientists with samples of microorganisms adapted to survive without sunlight and with limited nutrients. These lakes, and others like them, are windows into conditions that are extreme yet stable, offering insights into both life's resilience and the history of the continent. Beneath the ice, the topography is surprising. Mountain ranges extend under the frozen surface, some peaks piercing the ice to form nunataks, small islands of rock surrounded by white. Valleys are carved deep into the bedrock, creating channels through which glaciers flow, sometimes at surprising speeds. Rivers of meltwater run beneath the ice, forming networks that resemble familiar landscapes elsewhere on Earth, yet remain completely hidden. These features were formed long before the ice arrived, shaped by tectonic activity, erosion, and ancient climate patterns. Some valleys have remained frozen and undisturbed for tens of millions of years, preserving layers of sediment, rock, and evidence of ancient life. Mapping this hidden world requires specialized tools. Ground-penetrating radar sends waves through the ice and measures the signals that bounce back from underlying rock, water, and sediment. Satellites measure subtle changes in the ice's surface, revealing the movement of glaciers and the shapes of subglacial valleys. Seismic studies use controlled vibrations to understand the depth and structure of the bedrock below. These methods, combined with ice drilling and remote sensors, allow scientists to build detailed maps of landscapes that no human has ever walked upon. The images reveal surprises. Lakes in unexpected locations, rivers that flow beneath kilometers of ice, and mountains taller than many found on other continents. The implications for climate science are significant. The movement of glaciers depends on the shape and composition of the land beneath them. Deep valleys can guide ice toward the ocean more quickly, influencing the stability of ice shelves and the rate at which ice enters the sea. Subglacial lakes act as buffers, affecting ice flow and the response of the continent to warming conditions. By studying these hidden landscapes, scientists gain a better understanding of how Antarctica has changed over time and how it may respond in the future. Knowledge of these features improves models of global sea level rise giving humanity a clearer picture of what lies ahead as the climate shifts. Beyond climate, these ancient landscapes tell a story of Earth itself. The ice that covers Antarctica is young compared with the land underneath. Beneath the frozen surface, sediments contain fossils, minerals, and evidence of past climates. Some areas were once temperate, covered by forests, and inhabited by creatures that are now extinct. Rivers and lakes once flowed openly, and mountains were shaped by forces that continue to operate beneath the ice. Studying these features allows geologists and climatologists to piece together the planet's history, understanding how continents moved, how climates shifted, and how life adapted to changing conditions. Antarctica is not just a frozen wasteland. It is a record of Earth's transformation over hundreds of millions of years. Subglacial lakes, in particular, have become a focus of curiosity and study. These isolated water bodies are chemically distinct from surface lakes, often low in oxygen and rich in minerals leached from bedrock. Microbial communities living in these waters survive without sunlight, relying on chemical reactions and ancient organic matter for energy. Sampling these lakes provides clues about the limits of life on Earth, and by extension, the possibilities of life in similar extreme environments elsewhere, such as beneath the ice of Jupiter's moon Europa or Saturn's moon Enceladus. The existence of these lakes shows that life can endure in ways once thought impossible, hidden in cold, dark, and isolated worlds. The ice itself is a protective layer. Subglacial landscapes are shielded from atmospheric weather, ultraviolet radiation, and large-scale human disturbance. Sediments that might erode elsewhere are preserved, and ice sheets act as a barrier against external contamination. This preservation allows scientists to examine layers of rock and soil that provide insight into ancient tectonic movements, past temperatures, and chemical compositions. Even small details, like the orientation of mineral grains or the presence of microfossils, offer important clues to how the continent and the planet have evolved. As satellites scan the ice from orbit, they reveal patterns that hint at hidden structures below. Linear features in radar data suggest valleys and ridges, while circular depressions can indicate lakes or basins. Ice thickness varies dramatically, rising over mountains and dipping into hidden valleys. These measurements allow scientists to estimate water content, ice pressure, and potential pathways for glacial movement. By combining multiple techniques, researchers can create three-dimensional maps of a world that is otherwise inaccessible, revealing a complex network of landforms that has existed for eons. The discovery of ancient landscapes preserved under ice has challenged assumptions about Antarctica. Long considered a barren, frozen desert, the continent has been recognized as a repository of Earth's history. Layers of sediment beneath the ice contain evidence of past climates, flora, and even extinct animal life. Fossilized pollen, ancient soils, and remnants of freshwater ecosystems show that parts of Antarctica were once green and temperate, home to forests, rivers, and diverse life forms. These discoveries illustrate the dramatic changes the continent has undergone and highlight the ice's role as both a preserver and a recorder of time. Even the shape of the ice itself reflects the terrain beneath. Ice streams accelerate in deep troughs, slowing on ridges or shallow areas. Pressure ridges, crevasses, and ice cliffs often form where subglacial topography changes abruptly. Scientists study these features to understand both present dynamics and past events, using the ice as a lens to observe processes that have occurred over thousands of years. The relationship between ice and land is continuous, with each shaping the other, revealing patterns that are otherwise hidden from view. Some subglacial valleys and basins may extend for hundreds of kilometers, forming drainage systems for meltwater that eventually reaches the ocean. These channels are often fed by pressure-induced melting at the base of glaciers, where friction generates heat. Water collects in depressions to form lakes, and in some cases, it flows beneath kilometers of ice, guided by the contours of the bedrock. These hidden waterways influence ice movement and stability, creating dynamic conditions that are slowly observed through remote sensing and limited sampling. The mapping of these features is ongoing. Each new expedition, each improved radar system, and each satellite observation brings more detail to light. Patterns that were once invisible emerge, showing networks of subglacial lakes, ridges, and valleys. Ice-penetrating radar surveys, combined with GPS measurements of ice movement, allow scientists to monitor subtle shifts in the hidden terrain. These observations not only improve understanding of Antarctica itself, but also inform global models of ice dynamics and sea level projections. The hidden landscapes of Antarctica are also a reminder of the continent's isolation. Because these areas are so inaccessible, they remain largely untouched by humans. This isolation has preserved chemical and biological signatures that may have disappeared elsewhere on Earth. By studying these ancient environments, scientists gain insight into conditions that predate human influence, providing baseline data that can help distinguish natural processes from anthropogenic changes. The continent serves as a natural laboratory where the past and present intersect under layers of ice. Antarctica's buried mountains, valleys, and lakes represent extremes of preservation and isolation. Some features have remained unchanged for tens of millions of years, offering snapshots of ancient climates and ecosystems. The ice above acts as both shield and lens, enabling scientists to study long-term processes with minimal interference. These discoveries underscore the significance of the continent in understanding Earth's history and future, revealing that beneath the stark white surface lies a world of depth, complexity, and quiet persistence. Through continued study, the hidden landscapes of Antarctica provide insights into how ice interacts with land, how life can persist in extreme isolation, and how ancient conditions shape the planet. Each new discovery adds a layer of understanding to the vast puzzle of Earth's evolution. Beneath the frozen exterior, Antarctica is alive with history, water, and the slow but constant movement of ice that has preserved this secret world for millions of years, awaiting human curiosity and careful study. Beneath the surface of Antarctica, the ice is not simply frozen water. It is a record of the Earth's past, layer upon layer, capturing the atmosphere, particles, and environmental conditions of each year that has passed. Scientists call this ice a time capsule, a natural archive that preserves tiny bubbles of air, dust, and chemicals from ages long before humans walked the planet. Each meter of ice contains a story, and together, these layers stretch back hundreds of thousands of years, sometimes even more than 1 million, revealing the history of Earth's climate in exquisite detail. Ice cores are the key to unlocking this history. These long cylinders of ice are extracted from deep within the ice sheets using specialized drilling equipment designed to preserve the integrity of the layers. Some cores are more than 4 kilometers long, representing millions of years of snow accumulation compacted into solid ice. Drilling must be slow and precise, as the ice is fragile and can crack under pressure. The process involves a combination of rotary drills and hollow barrels that capture the ice while minimizing contamination. Once removed, cores are carefully transported in cold storage to laboratories around the world, where they are studied under controlled conditions that prevent melting or chemical change. Within the ice cores, trapped air bubbles provide a direct record of the atmosphere at the time the snow fell. By analyzing the composition of these bubbles, scientists can measure concentrations of carbon dioxide, methane, and other greenhouse gases over vast stretches of time. This allows researchers to track natural climate cycles, identifying periods of warming and cooling, and to understand how greenhouse gases correlate with temperature changes. Ice cores have revealed dramatic fluctuations in CO2 levels over hundreds of thousands of years, showing a rhythm of glacial and interglacial periods that shape the planet's climate before human influence. Temperature history is also encoded in the ice. The ratio of different oxygen and hydrogen isotopes in water molecules changes depending on the temperature when the snow formed. By examining these ratios at each layer, scientists reconstruct past temperatures with remarkable precision. The results show cycles of cold ice ages, warmer interglacial periods, and subtle shifts in climate that often preceded major changes in the environment. These records help explain how the Earth responds to natural forces, such as variations in solar energy, ocean currents, and volcanic activity, providing context for understanding current and future climate trends. Dust trapped in the ice adds another layer of information. Fine particles blown from continents by wind become embedded in snowfall, settling onto the ice and remaining locked for millennia. The chemical composition of this dust reveals the location of its origin, shedding light on past wind patterns, aridity, and environmental conditions on other continents. During colder periods, more dust is carried to Antarctica, reflecting the expansion of dry and windswept areas elsewhere. These records provide a detailed map of global climate dynamics, showing the interconnection between regions separated by thousands of kilometers. Volcanic eruptions also leave distinct marks in the ice. Layers containing high concentrations of sulfate and ash indicate large eruptions that sent particles high into the atmosphere. These deposits are often accompanied by brief cooling periods, as volcanic aerosols reflect sunlight and temporarily alter climate conditions. By dating these layers and matching them with known eruptions, scientists can build timelines of geological events and study their impact on global climate. Ice cores thus preserve both gradual changes and sudden events, giving a complete picture of Earth's environmental history. Cosmic dust and meteorite fragments also appear in the ice, adding a perspective from beyond Earth. Tiny particles fall through the atmosphere and become embedded in snowfall, remaining preserved for thousands or even millions of years. The composition of these particles can reveal information about the solar system, including changes in the influx of cosmic material and rare isotopes that trace the Earth's exposure to cosmic events. These layers, though often subtle, provide another window into forces acting on the planet from outside, complementing the story told by air bubbles and chemical composition. Scientists reconstruct climate history by combining all these pieces of evidence. Gas concentrations, isotopes, dust, and volcanic layers are carefully measured, compared, and aligned with other proxies such as ocean sediments and tree rings. The result is a continuous record that stretches back hundreds of thousands of years, revealing how the Earth's climate system has operated under different conditions. Patterns emerge: slow shifts in temperature, sudden cooling events, long warm periods, and correlations with greenhouse gas levels. This knowledge informs models of climate dynamics, helping predict how the planet might respond to ongoing human-driven changes. The oldest ice cores have been extracted from East Antarctica, where the ice is thick and the layers are well preserved. Some cores date back over 800,000 years, capturing nearly 1 million years of Earth's climate cycles. By studying these cores, scientists have identified repeated patterns of ice ages, warming periods, and the timing of transitions between them. They also show the natural range of greenhouse gas levels, providing context for the rapid increase in CO2 observed over the past century. The contrast between natural variations and current trends underscores the impact of human activity on the climate system. The structure of ice cores tells its own story. Layers vary in thickness, reflecting changes in snowfall from year to year. Summer snow may appear lighter and more compact, while winter snow is denser. Occasional melt layers indicate warmer periods, while dusty layers mark dry conditions. Careful examination of these features allows scientists to count years much like tree rings, providing precise chronologies. These chronologies are essential for correlating ice core data with other records of climate change, ensuring that interpretations are accurate and reliable. Each ice core also provides insight into the chemistry of past oceans and continents. Salts and other soluble ions deposited in snowfall reveal information about sea ice extent, ocean currents, and atmospheric circulation. High levels of sodium indicate strong sea spray, while elevated nitrate levels reflect changes in soil processes or atmospheric chemistry. These chemical markers allow researchers to reconstruct not only temperature and greenhouse gases, but also broader environmental conditions, creating a detailed portrait of Earth's climate system through time. The study of ice cores has revealed surprising events in Earth's past. Rapid warming periods, called interstadials, occurred in a matter of decades, changing ecosystems and ice sheet behavior. Sudden cooling events, sometimes linked to volcanic eruptions or shifts in ocean currents, demonstrate the sensitivity of the climate system. Even small variations, once considered insignificant, can have cascading effects on glaciers, sea levels, and ecosystems. These insights highlight the complexity and interconnectivity of Earth's climate and emphasize the importance of long-term records preserved in ice. Modern technology has expanded what can be learned from ice cores. Microscopes, spectrometers, and mass analyzers detect trace chemicals and isotopes with extreme sensitivity. DNA analysis identifies ancient microbial life trapped in the ice. Imaging techniques reveal fine layers, bubbles, and impurities invisible to the naked eye. These innovations allow researchers to extract more data from smaller samples, reducing the need for extensive drilling, while increasing the accuracy and depth of knowledge obtained from each core. The combination of air, water, dust, and chemicals in ice cores forms a multi-dimensional record. Scientists can read past temperature, greenhouse gases, volcanic activity, wind patterns, ocean behavior, and even extraterrestrial input from cosmic dust. Each layer is a page in a book written over millennia, detailing the natural rhythms of the planet, sudden disruptions, and the slow evolution of the climate system. By interpreting this record, humans gain a unique perspective on the forces that shape Earth's environment. Ice cores also inform our understanding of glacial dynamics. The density and structure of layers reveal past ice accumulation rates, flow patterns, and basal conditions. Variations in the ice indicate changes in snowfall, temperature, and wind over time. By studying these features, scientists can reconstruct not only climate, but also the history of ice sheet growth and retreat, understanding how Antarctica has responded to natural fluctuations in temperature. These insights are critical for predicting the continent's future behavior under current warming trends. Even subtle features in ice cores have meaning. Tiny bubbles or small chemical variations indicate short-lived events, such as volcanic eruptions or brief warm spells. Layers rich in dust suggest windier or drier conditions. The alignment and orientation of crystals provide information about ice deformation and flow. By combining all these details, researchers build a comprehensive picture of the Earth's environment at specific points in history. No single measurement tells the full story. It is the accumulation of layers, signals, and records that allows reconstruction of past climates. The long-term perspective provided by ice cores is unparalleled. While other climate records, like tree rings or sediments, may cover hundreds or thousands of years, Antarctic ice cores extend hundreds of thousands of years into the past. This allows scientists to observe cycles and patterns on timescales that are otherwise inaccessible, identifying the slow processes that shape Earth's climate and the rapid events that punctuate these trends. Ice becomes a mirror of Earth's environmental system, reflecting both stability and change with clarity and precision. By carefully interpreting ice core data, scientists can identify correlations between greenhouse gases, temperature, and sea level. The ice shows that increases in CO2 and methane often accompany warming periods, while decreases coincide with ice ages. Volcanic eruptions leave sharp spikes in sulfate levels, and cosmic dust layers mark extraordinary events. Together, these signals allow researchers to reconstruct a complex, interconnected story of Earth's climate, providing a foundation for understanding both past natural cycles and the impact of modern human activity. Through this frozen archive, Antarctica speaks of time in a language of layers, bubbles, and particles. It offers a record that spans generations far beyond human memory, detailing the rhythms of ice ages, the rise and fall of greenhouse gases, and the interplay of volcanic, atmospheric, and extraterrestrial forces. Each ice core is a chapter in this ongoing story, carefully preserved under kilometers of ice, waiting to be read and interpreted. Antarctica's ice is more than a barrier. It is a library of Earth's climate, a repository of knowledge that continues to guide humanity in understanding the planet's past, present, and future. Life in Antarctica exists at the edge of possibility, thriving in conditions that would destroy most organisms. On the surface, the continent is a vast expanse of ice and snow, extremely cold, dry, and exposed to intense ultraviolet radiation during summer months. Yet even here, life persists in surprising ways. Microbial communities inhabit the snow, ice, and hidden lakes beneath the glaciers. These microscopic organisms, sometimes numbering millions per gram of snow, survive with minimal nutrients and under extreme pressure and cold. They can remain dormant for years, only activating when conditions allow, and they often rely on chemical energy rather than sunlight to sustain themselves. Beneath the ice, subglacial lakes provide isolated habitats where life has endured for millennia. Lake Vostok, Lake Whillans, and other similar bodies of water host microbial life that relies on chemicals leached from rock and organic matter trapped within the ice. These organisms thrive in total darkness and extreme cold, some producing antifreeze proteins that prevent ice crystals from forming inside their cells. Their metabolism is slow, and growth occurs over years rather than days, but they maintain stable populations in environments that have remained unchanged for hundreds of thousands of years. Studying these microbes reveals strategies for survival in energy-limited and cold environments, offering insight into the resilience of life under extreme conditions. Antarctica's extremophiles provide examples of survival mechanisms that are both remarkable and varied. Some microbes produce thick protective cell walls, resisting damage from freezing and thawing cycles. Others form dormant spores that can survive desiccation, ultraviolet exposure, and chemical stress. Certain bacteria generate pigments that shield them from intense solar radiation during periods of summer light, while others rely on biofilms to trap moisture and nutrients in otherwise dry and barren ice. These adaptations are key to understanding the limits of life and how ecosystems persist when resources are scarce and conditions are harsh. Larger forms of life are concentrated near the coast, where the ice meets the ocean and nutrients are abundant. Seals, such as the Weddell and leopard seals, have adapted to survive both in water and on ice. Their thick layers of blubber provide insulation against freezing temperatures, while their large, strong flippers allow them to maneuver efficiently through icy waters. Breathing holes in sea ice are used strategically, allowing access to water for hunting and escape from predators. These adaptations illustrate a balance between energy conservation and survival, ensuring that seals can thrive in a challenging environment with seasonal extremes. Penguins are among the most recognizable Antarctic species, perfectly adapted to the cycles of light, darkness, and cold. Emperor penguins, in particular, breed during the harsh winter months, with males incubating eggs on their feet under thick layers of skin and feathers. Their social behavior, huddling together for warmth, demonstrates an evolved strategy to conserve heat and survive prolonged exposure to cold winds. Chicks are nourished with food stored in their parents' stomachs, and their growth is synchronized with seasonal changes, ensuring that fledging coincides with the summer abundance of fish and krill. These cycles are tightly linked to the environment, and any disruption can affect survival rates for generations. Krill, small crustaceans abundant in Antarctic waters, form the base of the food web. These tiny creatures feed on phytoplankton that blooms during the summer, taking advantage of sunlight that reaches the surface waters. Their populations fluctuate seasonally, growing rapidly during productive months and shrinking in winter, but they sustain a complex ecosystem, feeding penguins, seals, whales, and seabirds. Krill are adapted to survive in cold water, with high concentrations of proteins and fats that provide energy and insulation. Their migrations and swarming behavior demonstrate how even small organisms are finely tuned to the rhythms of Antarctic seasons. Seasonal migrations are a defining feature of life in Antarctica. Many birds, whales, and seals travel vast distances to exploit seasonal abundance. Some seabirds, like petrels, spend months at sea before returning to breeding colonies on the ice. Whales follow krill swarms, moving thousands of kilometers in search of food during winter and summer cycles. Even microscopic organisms are affected by these changes, with nutrient availability fluctuating according to ice cover, water movement, and light penetration. These cycles create a dynamic ecosystem, where energy flows from the sun through phytoplankton to krill, and then to larger predators. Each level of life adapted to the extremes of the environment and season. The adaptations seen in Antarctic life extend beyond survival. They also reveal evolutionary responses to extreme environmental stress. Ice algae grow on the underside of sea ice, absorbing sunlight and performing photosynthesis even under low-light conditions. Some microorganisms can metabolize sulfur, nitrogen, or iron compounds instead of relying on organic carbon. Fish in Antarctic waters have antifreeze proteins that prevent their blood from freezing, while some invertebrates enter suspended states to endure prolonged cold. These biological innovations demonstrate a wide range of solutions to the challenges posed by Antarctica's cold, dry, and highly variable conditions. Life in extreme conditions provides a laboratory for scientific discovery. Studying microbial communities in ice and subglacial lakes offers clues about the potential for life on other planets and moons where sunlight is limited or absent. The chemical pathways these organisms use to extract energy from minerals or trapped organic matter suggest that life can exist in environments previously thought uninhabitable. Antarctic extremophiles thus inform astrobiology, showing how life may persist in ice-covered oceans or beneath frozen crusts elsewhere in the solar system. The harsh environment of Antarctica also serves as a test of climate resilience. Species that survive the cold, fluctuations in food supply, and periods of complete darkness demonstrate strategies that may be useful in understanding ecological responses to changing climates elsewhere. By observing how organisms cope with extreme conditions, scientists can gain insight into potential responses to warming temperatures, changes in ice coverage, and shifts in ocean currents. These studies provide a framework for understanding the limits of biological adaptation and the potential consequences of environmental change on a global scale. Microbial life in ice cores and subglacial lakes also preserves historical records. DNA and chemical traces reveal past environmental conditions such as temperature, salinity, and nutrient availability. By comparing present-day communities to those preserved in ancient ice, researchers can infer changes in climate and ecosystem dynamics over thousands of years. These records not only illuminate past biological responses, but also help predict how species might adjust to future shifts in temperature, ice cover, and resource availability. Even small differences in the environment can have significant effects on Antarctic life. The thickness of ice above a subglacial lake, the salinity of seawater, or the timing of sunlight all influence growth rates, reproductive cycles, and survival strategies. Organisms have adapted to these nuances through specialized metabolism, flexible life cycles, and cooperative behaviors. Penguins huddle together, microbial colonies form biofilms, and krill swarm collectively, all reflecting the fine-tuned responses necessary to survive in a place where the margin for error is narrow. Life in extreme conditions demonstrates both fragility and resilience. While organisms are highly adapted, they remain vulnerable to changes in temperature, ice coverage, and food availability. Disruptions such as ice shelf collapse, warming oceans, or shifts in krill populations can ripple through the ecosystem. Yet, the persistence of microbial life in subglacial lakes and ice cores shows that resilience exists at multiple scales. From microscopic organisms to large mammals, sustaining ecosystems even in one of the harshest environments on Earth. Seals and penguins provide vivid examples of adaptation and survival. Their physical traits, reproductive strategies, and behavioral patterns are all closely tied to the Antarctic environment. Blubber, feathers, and fur offer insulation. Careful timing of breeding ensures that young are born during periods of maximum food availability, and social behaviors reduce energy loss and increase survival chances. Each of these strategies has evolved over generations to meet the demands of extreme cold, strong winds, and seasonal scarcity. The Antarctic food web is tightly linked to environmental cycles. Phytoplankton grow when sunlight penetrates the ocean surface, feeding krill, which then support penguins, seals, and whales. Each species relies on the abundance and timing of resources, and disruptions can have cascading effects. Seasonal migrations ensure that predators find food, while prey populations adjust to changing availability. Even microscopic organisms respond to shifts in ice cover, salinity, and nutrients, reflecting the interconnectedness of life in extreme conditions. Research in Antarctica continues to reveal new species and previously unknown adaptations. Microbes discovered in subglacial lakes, isolated for hundreds of thousands of years, possess unique enzymes and metabolic pathways that challenge existing knowledge of biology. Scientists study these organisms not only for curiosity, but also for potential applications such as biotechnology, medicine, and understanding life's capacity for resilience. Each discovery emphasizes the remarkable diversity and ingenuity of life in extreme conditions. The harsh environment does not prevent complexity. Microbial mats, sea ice communities, and subglacial ecosystems display interactions between species, nutrient cycling, and energy transfer. Life organizes itself around available resources, forming networks that sustain populations through scarcity and abundance. Observing these patterns in Antarctica allows scientists to see ecosystems functioning in near pristine conditions, providing insight into fundamental ecological principles that might be masked in more temperate or human-impacted environments. Even in the depths of winter, when darkness and cold dominate, life persists. Penguins incubate eggs and protect chicks in extreme cold. Krill remain in the water below sea ice, and microbes continue slow metabolism in ice and lakes. These organisms endure periods of minimal activity, only becoming more active when conditions improve. Their ability to pause and resume life cycles demonstrates an important survival strategy that allows persistence in an environment governed by extreme seasonality. Antarctica's extreme conditions provide a mirror to understand life itself. The adaptations seen in seals, penguins, krill, and microbes illustrate a wide range of survival strategies. Physical traits, behavioral patterns, metabolic flexibility, and dormancy all contribute to persistence under cold, dry, and nutrient-limited conditions. Studying these adaptations informs not only ecological understanding, but also practical considerations for human survival in extreme environments, from polar research stations to space missions. In this frozen land, life is both fragile and persistent. Microbial colonies survive without sunlight. Animals endure cold and hunger, and ecosystems operate under precise seasonal rhythms. Each species, from the smallest microbe to the largest predator, is a testament to adaptation and resilience. The study of life in Antarctica provides insight into the limits of survival, the interplay between organisms and environment, and the remarkable ways that life endures where most would perish. It is a living demonstration of the power of adaptation, the complexity of ecological networks, and the subtle persistence of existence under conditions that are extreme yet sustaining. Antarctica is not only a frozen continent, it is a regulator of the Earth's climate, a massive reservoir of ice that affects oceans, weather, and temperature patterns across the planet. The Antarctic ice sheet contains enough frozen water to raise global sea levels by more than 50 meters if it were to melt entirely, a scale of impact that few other regions could match. Ice sheet dynamics, the processes that control the growth, flow, and melting of the ice, are complex and vary across the continent. In some areas, glaciers move slowly over bedrock, while in others, ice streams flow rapidly toward the coast, carrying enormous volumes of ice into the ocean. These movements are influenced by temperature, snow accumulation, subglacial water, and the topography of the bed beneath the ice. Melting patterns in Antarctica are not uniform. The West Antarctic ice sheet is particularly vulnerable, with portions grounded below sea level and therefore more sensitive to warming oceans. Satellite observations show thinning ice in several regions, where glaciers accelerate and ice shelves retreat, In contrast, parts of East Antarctica remain thick and stable, although small changes are detected even there. Seasonal melting occurs mainly at the edges of the continent, forming melt ponds and streams. But long-term changes in temperature, ocean currents, and ice shelf stability can trigger larger-scale ice loss. The balance between accumulation in the interior and loss at the edges determines the continent's overall contribution to sea level. When Antarctic ice melts or calves into the ocean, it affects sea levels worldwide. Even small changes in the ice sheet can raise coastal waters, threatening populations and ecosystems far from the polar regions. Icebergs that break off can drift thousands of kilometers, influencing ocean currents and the mixing of cold and warm waters. As ice enters the ocean, it contributes fresh water that alters the density and salinity of seawater, affecting the circulation of currents like the Antarctic Circumpolar Current. This circulation, in turn, drives climate patterns and nutrient distribution in the Southern Ocean, connecting Antarctica's changes directly to global weather and ecosystem health. Antarctic melting also influences weather beyond the continent. Changes in ice volume and ocean currents can alter atmospheric circulation, shifting wind patterns and storm tracks. Regions in the Southern Hemisphere experience changes in rainfall, temperature, and seasonal weather due to Antarctic conditions. Even continents in the Northern Hemisphere are affected, as shifts in ocean currents impact the movement of heat and moisture around the planet. The interconnectedness of Antarctic ice, oceans, and atmosphere illustrates that no change in this remote region remains isolated. The effects ripple globally, often in ways that are slow, subtle, or delayed. Historical baselines provide perspective on current changes. By examining ice cores, sediment records, and historical satellite imagery, scientists can determine how Antarctica's ice sheets behaved over centuries and millennia. These records show that the ice has waxed and waned in response to natural climate cycles, including variations in solar energy, volcanic activity, and greenhouse gas concentrations. Comparing current observations to these baselines allows researchers to detect anomalies and assess whether recent changes fall within natural variability or indicate a trend driven by human influence. Modern data suggests that recent ice loss is occurring at an unprecedented rate, particularly in West Antarctica, highlighting the continent's sensitivity to warming conditions. Satellite technology has revolutionized our understanding of ice sheet dynamics. Remote sensing allows continuous monitoring of ice thickness, velocity, and surface elevation changes. Radar and laser altimetry measure ice surface heights, revealing areas of thinning or thickening. GPS sensors track glacial movement with remarkable precision. Oceanographic instruments measure temperature and salinity beneath ice shelves, providing data on melting from below. Combining these tools, scientists can create detailed models of ice sheet behavior, simulating potential scenarios for sea level rise and global climate impact. Scientific debates continue regarding the rate and magnitude of Antarctic changes. Some researchers argue that rapid ice loss in certain regions may trigger unstable retreat, potentially leading to accelerated sea level rise. Others caution that uncertainties remain in modeling ice-ocean interactions and predicting feedback loops. The grounding line, where ice meets bedrock below sea level, is particularly critical. If this line retreats, ice above may become unstable, increasing flow into the ocean. The interaction of ice shelves, ocean currents, and subglacial water is complex, and small differences in temperature or melt rates can produce large effects over decades. Observations show that ice shelves play a key role in stabilizing glaciers. These floating extensions of the ice sheet act as brakes, slowing the flow of inland glaciers. When ice shelves thin or collapse, glaciers accelerate, sending more ice into the ocean. Larsen B, an ice shelf in the Antarctic Peninsula, partially collapsed in the early 2000s, triggering rapid glacier acceleration and significant local ice loss. Such events illustrate how interconnected systems can shift quickly, and why understanding ice shelf dynamics is essential for predicting the continent's contribution to sea level. The Southern Ocean is both a buffer and a driver of change. Cold, dense waters surround Antarctica, regulating heat exchange between ocean and atmosphere. Melting ice introduces fresh water, lowering salinity and affecting the formation of deep water masses that drive global ocean circulation. Changes in these processes can modify climate patterns far from the poles, affecting rainfall, storms, and temperature distributions worldwide. Ice loss, ocean mixing, and atmospheric feedback are linked, forming a complex system in which Antarctica is both a source of stability and a potential trigger for change. Temperature changes in the polar regions are amplified compared to the global average, a phenomenon known as polar amplification. Even small increases in ocean or air temperature can lead to accelerated melting, reduced ice cover, and shifts in albedo, the reflectivity of the surface. When ice and snow decrease, darker rock and ocean absorb more sunlight, increasing warming in a feedback loop. These dynamics highlight the vulnerability of the Antarctic system and its influence on global energy balance. Models of future change rely on current observations, historical records, and physical principles. By simulating ice sheet behavior under different warming scenarios, scientists can estimate potential contributions to sea level rise. Projections vary depending on greenhouse gas emissions, ocean warming, and ice shelf stability, but even conservative estimates indicate measurable impacts over the coming century. These models are refined continuously as new data become available, allowing more accurate predictions of Antarctic ice sheet behavior and its global consequences. The interplay between ice, atmosphere, and ocean is crucial for understanding climate feedbacks. When ice melts, it changes the density and temperature of the surrounding water, which can accelerate glacial retreat. Ice sheet elevation affects atmospheric circulation and local temperature patterns. Wind patterns influence snowfall and ice accumulation, while ocean currents regulate basal melting of ice shelves. These feedbacks demonstrate that Antarctic ice is not passive, but actively interacts with multiple components of the Earth system, influencing both regional and global climate. Observations also reveal variations in ice sheet response. Some glaciers are retreating quickly, while others remain stable or even advance slightly. Differences in underlying topography, ocean heat, and ice thickness contribute to this variability. These nuances illustrate that Antarctica is not a uniform system, but a mosaic of dynamic regions, each responding differently to environmental pressures. Understanding these variations is key to predicting the continent's overall impact on sea level and climate. Ice loss in Antarctica is already measurable. Satellite altimetry shows surface lowering, while gravimetric measurements detect changes in mass. These observations, combined with in situ measurements, confirm that some regions are losing ice at rates exceeding several meters per century in water equivalent. The cumulative effect contributes to rising sea levels and changes in ocean circulation. Even small changes in Antarctica can have amplified effects due to the continent's size and the interconnectedness of the Earth system. Antarctica's influence on global climate extends beyond sea level. Its cold air masses shape atmospheric circulation, driving winds and weather patterns across the southern hemisphere. The position of the Antarctic circumpolar current controls heat transport and nutrient distribution in oceans. Ice loss can shift these currents, altering climate patterns in distant regions, from South America to Africa to Australia. The continent's ice acts as both regulator and indicator, reflecting the health of the global climate system. Current research emphasizes monitoring and prediction. Continuous satellite observation, field measurements, and ice core studies provide a detailed record of changes. Scientists track ice thickness, glacier speed, ice shelf extent, and ocean temperatures to detect trends and anomalies. These efforts allow early identification of destabilizing processes and help refine models that forecast future scenarios. The combination of observation and modeling is critical for understanding how Antarctica will respond to ongoing warming and how that response will propagate through the Earth system. Despite its remoteness, Antarctica's changes are deeply relevant to humanity. Rising seas threaten coastal communities, shifting ocean currents impact fisheries, and altered weather patterns affect agriculture and ecosystems worldwide. Understanding ice sheet dynamics and projecting their future behavior is essential for adaptation and mitigation strategies. Scientific study of the continent provides both warnings and guidance, showing how interconnected a distant frozen land can be with life across the planet. The Antarctic ice sheet is a mirror of the past and a predictor of the future. By examining ice flow, melting patterns, and ocean interactions, scientists gain insight into natural variability, human impact, and potential tipping points. These lessons are critical for understanding how fragile or resilient the global climate system is in the face of change. The continent, vast and isolated, serves as both a laboratory and an early warning system, revealing processes that affect the entire Earth. Through careful observation and study, researchers continue to unravel the complexities of Antarctic ice and its influence on global climate. From subglacial lakes to ice shelves, from glaciers to the Southern Ocean, every part of the continent interacts with the wider world. Understanding these connections helps humanity anticipate and prepare for change, revealing the essential role Antarctica plays in stabilizing and regulating the planet's environment. Its frozen expanse, dynamic ice, and interacting systems make it both a critical monitor of past and present conditions and a key predictor of future global impacts. Human presence in Antarctica has always been limited by the harshness of the environment. For centuries, the continent remained a distant, unknown land, hidden beneath ice and cloud. Early explorers faced unimaginable challenges, navigating icy seas, braving freezing temperatures, and enduring months of darkness. The heroic age of Antarctic exploration in the late 19th and early 20th centuries marked a turning point in human interaction with the continent. Expeditions led by figures such as Roald Amundsen and Robert Falcon Scott captured the world's attention. Amundsen, using careful planning, skis, and sled dogs, reached the South Pole in 1911. Scott arrived shortly after, facing extreme conditions that ultimately claimed his life and those of his team. Their journeys were defined by courage, endurance, and the struggle to survive in one of the most inhospitable regions on Earth. These early expeditions provided more than heroic stories. They laid the groundwork for scientific understanding. Explorers documented ice, formations, collected geological samples, and observed weather patterns. Despite the dangers, their records became valuable references for future research. Mapping coastlines, measuring elevations, and noting environmental conditions helped later scientists understand the scale and dynamics of the Antarctic landscape. These pioneering efforts demonstrated both the challenges and the possibilities of working in extreme polar conditions. The Antarctic Treaty System, signed in 1959 and entering into force in 1961, created a framework for international governance. The treaty set aside the continent for peaceful purposes, prohibiting military activity, mineral exploitation, and territorial claims. It established that scientific research should be encouraged and shared freely among nations. Today, the treaty remains a cornerstone of Antarctic management, ensuring that the continent is preserved for research, environmental protection, and collaboration rather than national competition. Its success lies in fostering cooperation, creating a system where countries work together to understand and protect this remote land. Modern research stations are scattered across the continent, both along the coasts and deep within the interior. These stations are often built to withstand extreme cold, high winds, and isolation, equipped with insulated shelters, generators, and communication systems. Scientists live in these stations for months at a time, conducting research in glaciology, climate science, biology, and geology. Supplies are delivered by ship or aircraft, sometimes only once or twice per year, making planning and logistics critical. Stations must maintain sufficient fuel, food, and medical provisions, while also preparing for emergencies in a region where evacuation is difficult and weather conditions can delay travel for days or weeks. Life at research stations involves adaptation to isolation and harsh conditions. During winter months, temperatures can fall well below -50 degrees Celsius, winds howl across ice fields, and darkness prevails for months. These conditions create psychological stresses that must be managed carefully. Scientists and support staff often work in small groups, relying on routine, communication, and shared responsibility to maintain morale. Activities are structured to provide purpose and interaction, from scheduled research tasks to recreational pursuits. Sleep, nutrition, and social engagement are monitored closely to reduce the effects of prolonged isolation and environmental stress. The physical environment itself presents challenges. Frostbite, hypothermia, and fatigue are constant risks. Movement outside the station requires protective clothing, careful navigation, and awareness of crevasses hidden beneath snow. Even minor equipment failure can become serious in such extreme settings. Weather forecasting and communication systems are vital to ensure safety, allowing stations to plan excursions and research operations. Each day involves a balance between scientific objectives and the practical need to survive and maintain the station infrastructure. International collaboration is a hallmark of Antarctic research. Scientists from multiple countries work together, sharing data, laboratory space, and logistical resources. Research on climate, ecosystems, and geology often involves multinational teams combining expertise from different fields. Projects like ice core drilling, satellite observations, and oceanographic studies are coordinated to maximize efficiency and minimize duplication of effort. This cooperation reflects the spirit of the Antarctic Treaty, promoting science above national competition and ensuring that knowledge gained is shared for the benefit of all humanity. Stations vary in design, depending on location and purpose. Coastal stations often support marine biology, oceanography, and meteorology, while interior stations focus on glaciology, atmospheric, chemistry, and ice core sampling. Some are permanently staffed, while others are seasonal, operating only during summer months when conditions allow easier access. The infrastructure must withstand extreme cold, high winds, and shifting ice, Buildings are often raised to prevent snow accumulation, insulated to retain heat, and designed to allow maintenance with minimal exposure to dangerous conditions. Logistical challenges are immense. Fuel must be transported across hundreds of kilometers, often over treacherous ice or by specialized aircraft. Fresh water is limited, usually obtained by melting snow. Power is generated by diesel generators, wind turbines, or solar panels, with redundancy systems to ensure continuity. Medical facilities are basic, requiring stations to be prepared for emergencies until evacuation is possible. Communication with the outside world is maintained through satellite links, enabling coordination, emergency response, and connection with family and colleagues thousands of kilometers away. The human presence has gradually expanded from early exploration to permanent research. Today, over 50 nations maintain some form of station or field camp in Antarctica, with populations peaking at around 4,000 during the summer. Winter populations drop significantly, sometimes to a few hundred, highlighting the extreme conditions that limit access. Each station is a hub of scientific activity, carefully planned to operate in isolation, while contributing to global understanding of the continent. Living in isolation in Antarctica has shaped both behavior and research methods. Routine is critical, and every task is planned for safety and efficiency. Psychological support is provided, including structured social activities, communication with family, and opportunities for personal projects. Small group dynamics are closely observed to prevent conflict and maintain collaboration. Even minor disagreements can escalate in confined, isolated settings, so training in teamwork and stress management is essential. Environmental stewardship is central to station operations. Waste disposal is strictly controlled, with most materials removed from the continent. Fuel spills, chemical contamination, and human impact on local ecosystems are minimized through careful planning and adherence to international guidelines. Stations operate as models for sustainable human activity in extreme environments, showing that scientific work can coexist with environmental preservation. Research conducted at these stations is wide-ranging. Glaciologists study ice cores and ice sheet movement. Climatologists monitor atmospheric changes. Biologists examine extremophiles and wildlife, and geologists investigate rock formations and subglacial landscapes. Oceanographers study the Southern Ocean and its currents, while astronomers take advantage of clear skies and minimal light pollution. The data gathered informs global climate models, ecosystem management, and our understanding of Earth's history. International collaboration extends beyond individual stations. Scientific committees coordinate research programs, share findings, and develop standards for data collection. Joint projects often involve multiple nations, combining resources and expertise to study complex systems like ice-ocean interactions, global climate, or migratory wildlife patterns. Conferences and publications ensure that results are widely accessible, fostering a culture of openness and cooperation in a region where national claims are set aside in favor of shared knowledge. The Antarctic Treaty also governs human activity beyond research. Mining, military activity, and territorial claims are prohibited, ensuring that stations operate within a legal framework that prioritizes science and peace. Regular inspections and reporting maintain accountability, with participating nations responsible for enforcing environmental standards and treaty obligations. This framework allows scientists to focus on research, confident that their work contributes to a global effort, rather than a competitive or extractive enterprise. Research stations also act as observation posts. Meteorological data, satellite calibration points, and long-term monitoring programs rely on these locations to maintain continuous records. This information is crucial for understanding climate change, ice dynamics, and ecosystem shifts. The human presence, though small compared to the continent's scale, is carefully integrated into a larger network of observation, allowing continuous data collection in one of the most remote regions on Earth. Stations are often seasonal, reflecting the extreme contrast between Antarctic summer and winter. Summer provides continuous daylight, more moderate temperatures, and access by ship or aircraft. Scientists can travel farther, sample more locations, and conduct experiments that require outdoor exposure. Winter brings darkness, extreme cold, and logistical limits, concentrating human activity within station boundaries. These seasonal rhythms dictate research schedules, staffing, and operational planning, demonstrating the interplay between human activity and the natural environment. The human presence in Antarctica, though limited, has transformed the continent from an unexplored wilderness to a hub of scientific discovery. Early exploration set the stage, heroic yet dangerous, while modern stations provide stable platforms for research and observation. International treaties and collaboration ensure that activity is peaceful, coordinated, and environmentally responsible. Living in isolation under extreme conditions tests human endurance and ingenuity, while the work conducted contributes to knowledge that reaches across the globe. Every research station is a microcosm of human adaptation to extreme conditions. Engineers, scientists, and support staff live and work together, managing resources, safety, and productivity in a place where the margin for error is narrow. Supply chains, communications, and emergency planning are integral to daily life. Psychological and environmental stresses are mitigated through structure, social cohesion, and training. In this environment, human presence is both a challenge and a triumph, illustrating the possibilities of sustained activity on a remote and harsh continent. Antarctica is therefore both a laboratory and a stage. It tests human endurance, advances scientific understanding, and provides insights into environmental stewardship. Research stations, treaties, and international collaboration ensure that this fragile and extreme environment is respected, studied, and preserved. The continent's remoteness emphasizes the importance of careful planning, cooperation, and observation, making human presence in Antarctica a model for scientific engagement and global collaboration in one of the planet's last frontiers. Antarctica, often seen as a remote and untouched land, is increasingly revealing the hidden hazards and environmental threats it faces. Though isolated, the continent is not immune to the pressures of a changing world. Climate change, driven by rising greenhouse gases and global warming, is altering temperature patterns and ice stability. Even small increases in air and ocean temperature have pronounced effects on ice shelves, glaciers, and sea ice. Some ice shelves that were considered stable for centuries have begun thinning, fracturing, and collapsing, demonstrating how sensitive the system is to changes that might seem minimal from a human perspective. Glacial retreat is a particularly concerning hazard. Glaciers that flow into the ocean carry enormous volumes of ice, and when the buttressing ice shelves weaken or vanish, these glaciers can accelerate dramatically. The collapse of the Larsen B ice shelf in 2002 provides a stark example. Within months, glaciers feeding the shelf sped up, sending ice into the ocean and raising local sea levels. Events like this show that Antarctica can change quickly, defying expectations based on decades of apparent stability. Scientists continuously monitor glaciers with satellites and radar, Yet predicting sudden shifts remains challenging because so many variables, ice thickness, bedrock topography, subglacial water, interact in complex ways. Human activity, though limited, also introduces hazards. Research stations, supply routes, and ships bring fuel, chemicals, and materials into sensitive environments. Strict regulations minimize spills and contamination, but accidents still happen, and pollutants can persist in cold environments for decades. Fossil fuel residues from generators, waste incineration, and transport vehicles accumulate in snow, ice, and coastal waters. Once released, these contaminants are slow to break down, entering the food web and potentially affecting both microorganisms and larger animals. Even the most remote areas are affected, as wind and ocean currents transport pollutants long distances across the continent. Microplastics are another growing concern. Tiny plastic particles, transported by ocean currents and atmospheric deposition, have been found in Antarctic waters, sea ice, and even snow on the interior ice sheet. These particles originate from human activity thousands of kilometers away, yet accumulate in the polar environment due to global circulation patterns. Microplastics can be ingested by krill, fish, and birds, introducing toxins into the food web. The effects on wildlife are still being studied, but evidence suggests that bioaccumulation could disrupt physiological processes, reproduction, and overall ecosystem health. Antarctica's seeming remoteness does not protect it from global pollution. Rather, it underscores the reach of human impact. Ice shelf collapse presents dangers beyond immediate glacial acceleration. When massive ice shelves fracture, the sudden release of ice can trigger tsunamis or influence ocean currents locally. These events can disturb marine ecosystems, altering habitat and food availability for species dependent on stable sea ice. The loss of ice shelves also reduces the natural breaking effect on inland glaciers, increasing the volume of ice reaching the ocean and raising sea levels globally. These interactions highlight that Antarctica's power is not limited to its physical size. The continent's dynamics ripple across oceans, influencing climates and ecosystems far from the pole. Unexpected glacial events are often hidden beneath the surface. Subglacial lakes and water channels can lubricate ice movement, sometimes leading to sudden shifts or collapses. Radar and satellite monitoring have revealed bursts of glacial motion, where ice moves faster than predicted for short periods. These pulses can destabilize nearby ice shelves and produce unpredictable changes in flow patterns. The hidden nature of these hazards emphasizes that much of Antarctica's behavior occurs out of sight, beneath kilometers of ice, and requires careful observation and modeling to understand. Climate change also affects seasonal patterns in Antarctica. Changes in sea ice extent, snowfall, and wind patterns alter habitats for wildlife. Penguins, seals, and other ice-dependent species rely on predictable ice conditions for breeding, hunting, and shelter. When ice melts too early or fails to form adequately, populations can suffer from food scarcity, exposure, or increased predation. Even microscopic life in snow and subglacial lakes experiences shifts in nutrient availability and chemical balance, demonstrating that environmental changes cascade through ecosystems at all scales. Melting ice releases trapped gases and chemicals accumulated over millennia. Nitrous oxide, methane, and other trace gases preserved in ice can be liberated as temperatures rise, contributing further to greenhouse gas levels and altering chemical composition in local air and water. This process, while relatively small in global terms, demonstrates a feedback loop where ice loss can accelerate environmental change. Combined with the effects of ocean warming and ice shelf instability, Antarctica's response to climate change is both complex and profound. Pollution also reaches Antarctica indirectly. Aerosols and black carbon from industrial activity in other continents travel long distances in the atmosphere, depositing on ice and snow. Dark particles reduce surface reflectivity, increasing absorption of sunlight and accelerating melting. Even small quantities of deposited pollutants can have measurable effects on ice sheet stability and local climate. These inputs demonstrate how human activity in one part of the world can have unexpected consequences for distant ecosystems. Extreme weather events, amplified by climate change, pose additional hazards. High winds, sudden blizzards, and storms can dislodge ice, create dangerous crevasses, and disrupt both wildlife and human activity. Coastal areas experience strong waves that can erode ice cliffs or interfere with breeding grounds. Weather systems are increasingly unpredictable, and the combination of warming, changing wind patterns, and ocean dynamics creates conditions that are both hazardous and difficult to forecast. Marine ecosystems face threats from ocean acidification as well. Carbon dioxide absorbed by the Southern Ocean lowers pH levels, affecting calcifying organisms like krill, mollusks, and plankton. These organisms form the foundation of the Antarctic food web, so even small disruptions can cascade through predators such as penguins, seals, and whales. Combined with warming waters and changing ice cover, ocean acidification compounds the stress on Antarctic ecosystems, highlighting the interconnectedness of chemical, physical, and biological factors. Tourism, though relatively small in scale, introduces additional challenges. Visitors arrive by ship or plane, sometimes venturing onto fragile coastal ecosystems. Strict protocols minimize disturbance and waste, but the cumulative impact of human presence is measurable. Wildlife may be disturbed, microplastics or pollutants introduced, and accidental contamination occurs despite precautions. These pressures illustrate the delicate balance between scientific, recreational, and conservation priorities in Antarctica. Antarctica's hidden hazards serve as a warning about underestimating the continent's power. Its ice holds enormous energy, capable of rapid changes that influence global sea levels. Its weather can shift suddenly, and its ecosystems are finely tuned to extremes. Even small perturbations can produce amplified effects, demonstrating that human understanding and management must be cautious and informed. Scientific monitoring, careful logistics, and international cooperation are essential to mitigate these risks. Lessons from Antarctica extend to global environmental management. The continent demonstrates how distant regions are connected through climate, ocean, and atmospheric systems. Pollution, warming, and ice loss do not remain confined. They influence ecosystems, weather, and human societies worldwide. The study of Antarctic hazards provides insight into the consequences of inaction, the importance of observation, and the need for coordinated global responses to environmental challenges. Researchers continue to monitor microplastics, chemical contaminants, and ice dynamics, combining satellite imagery, in situ measurements, and biological studies. Data reveal patterns of accumulation, transport, and impact, illustrating that even remote regions are affected by global activity. Understanding these processes allows scientists to identify thresholds, predict cascading effects, and inform policy for both Antarctic management and broader environmental stewardship. The unpredictability of ice, shelf collapse, and glacial surges highlights the need for adaptive management. Unexpected events, such as the sudden calving of icebergs or bursts of glacial movement, demonstrate that rigid assumptions about stability are dangerous. Continuous observation, early warning systems, and flexible planning are necessary to respond to these threats, both for human operations and for understanding ecological impacts. Environmental threats in Antarctica also emphasize the importance of long-term research. Changes in ice thickness, chemical composition, and wildlife populations occur over decades and centuries. Only by maintaining continuous study can scientists detect trends, identify causes, and make informed predictions. This research is crucial not only for local understanding, but for global climate models and environmental policy. The combined effects of climate change, human activity, and natural hazards reveal that Antarctica is far from an inert wilderness. It is a dynamic system capable of sudden and far-reaching impacts. Ice sheets respond to warming oceans, pollutants travel across continents, and ecosystems shift under changing conditions. Understanding these threats requires integrated study, careful observation, and international collaboration. The lessons learned in Antarctica are relevant for global environmental management, offering a window into the consequences of human influence and natural variability. Antarctica's hidden hazards remind us that extreme environments hold both beauty and danger. Melting ice, shifting glaciers, pollutants, and fragile ecosystems interact in ways that are complex and often surprising. Awareness of these factors, combined with scientific research, careful logistics, and environmental policies, provides a path for protecting this remote continent. At the same time, it highlights the broader principle that no region is truly isolated, and that environmental stewardship requires a global perspective, informed by observation, evidence, and precaution. The continent's environmental threats underscore the importance of balance. Human presence must be minimal and carefully managed. Science must proceed with caution, and policies must enforce conservation and safety. Antarctica demonstrates that even a seemingly untouched land is vulnerable to subtle changes, and that small interventions can produce lasting consequences. It is a stark reminder that understanding and respect are essential for survival, both for life on the continent and for human society, which depends on the stability of global systems influenced by Antarctic conditions. Beneath the thick ice, Antarctica holds a geological history that stretches for hundreds of millions of years. The continent is a record of ancient processes where rocks, fossils, and landforms preserve the story of Earth's deep past. Today, much of this history remains hidden, covered by kilometers of ice. Yet scientists have been able to uncover fragments that reveal a dynamic and changing land. Geological studies show that Antarctica was once part of supercontinents, connected to regions that are now South America, Africa, India, and Australia. The movement of tectonic plates over hundreds of millions of years shaped the continent's mountains, valleys, and sedimentary basins, leaving a complex mosaic of rock formations. Rock outcrops along the Antarctic Peninsula and in other exposed regions provide windows into ancient landscapes. Igneous rocks, formed from cooled magma, reveal past volcanic activity, while sedimentary layers preserve evidence of rivers, lakes, and swamps that existed long before the ice sheet formed. These formations show that Antarctica was once much warmer, supporting forests, rivers, and diverse ecosystems. Fossilized plants, including ferns, conifers, and early flowering species, demonstrate that the continent was covered in lush vegetation during periods of the Mesozoic and Paleozoic eras. Fossilized pollen and spores preserved in sedimentary rock give insight into the climates of the distant past, revealing how temperature, rainfall, and atmospheric composition shifted over millions of years. Antarctica has also yielded remarkable fossil discoveries. Dinosaur bones, footprints, and ancient flora have been found in coastal outcrops, illustrating that the continent supported large terrestrial animals when it was part of the supercontinent Gondwana. Fossils of herbivorous dinosaurs indicate that forests and wetlands provided abundant food, while predatory species suggest complex ecosystems. These discoveries provide direct evidence that Antarctica's environment was once dramatically different from today's frozen desert, and they help scientists reconstruct the distribution of species across ancient landmasses. Meteorites offer another avenue into Antarctica's geological secrets. The continent's ice acts as a natural collector, preserving fragments of rock that fell from space and concentrating them on the surface. Over tens of thousands of years, meteorites embedded in ice are exposed by wind, melting, and ice movement, creating deposits that are accessible to researchers. These space rocks provide insight into the formation of the solar system, the composition of other planets, and the history of cosmic events. Because the ice preserves them in relatively pristine condition, Antarctica is one of the best places on Earth to study meteorites and connect Earth's history to events in space. Geological timescales in Antarctica are vast. Some of the oldest rocks, found in the East Antarctic Craton, date back over 3 billion years, providing evidence of early continental formation and crustal evolution. These ancient formations record processes such as continental collision, mountain building, and erosion, which shaped the Earth's crust long before humans existed. By studying these rocks, scientists gain perspective on the long-term evolution of continents and the dynamic nature of Earth's lithosphere. The ice itself acts as both a protector and a preserver. Ice sheets cover sedimentary basins, volcanic deposits, and glacial moraines, keeping them safe from erosion, weathering, and biological disturbance. In areas where ice has retreated, previously buried rocks and fossils are revealed, allowing researchers to study layers that have been shielded for millions of years. Subglacial drilling also recovers sediments and rock cores, revealing the chemical and physical history of buried landscapes. These frozen archives provide direct evidence of climate, tectonic activity, and biological presence long before human observation was possible. Antarctica's geology is not static. Ice movement continues to reshape the surface, exposing new rocks while transporting fragments across the landscape. Glacial abrasion smooths rock surfaces, while subglacial erosion carves valleys and channels. Mountains, some hidden beneath ice, influence ice flow and create microclimates that preserve distinct geological features. This ongoing interaction between ice and rock makes Antarctica a living laboratory, where ancient history and present-day processes coexist. Understanding Antarctica's geological past informs broader Earth science. The continent's role in supercontinent cycles, climate transitions, and ocean formation has implications for global geology. Studying its rocks and fossils helps reconstruct plate movements, predict mineral formation, and understand the evolution of Earth's surface. Antarctica serves as a key reference for comparing geology across continents, linking fossil records, rock sequences, and tectonic events to build a complete picture of Earth development over billions of years. The preservation of fossils, meteorites, and rock layers beneath ice emphasizes the continent's role as a natural archive. Ice shields delicate structures from decay, water, and wind, allowing scientists to recover evidence that would be lost in other regions. This combination of frozen protection and gradual exposure through ice dynamics provides a rare opportunity to study Earth's deep history directly, with minimal disturbance. Every discovery, from dinosaur footprints to ancient minerals, adds a piece to the puzzle of how continents formed, climates shifted, and life evolved on our planet. Even subtle geological features hold significance. Minor sedimentary layers can reveal periods of volcanic ash deposition, changes in river systems, or shifts in climate. Subtle folds and fractures in rock indicate tectonic stress and historical movement. Each observation contributes to the overall understanding of Antarctica's formation, the forces that shaped it, and the broader patterns of Earth's geology. Because the continent remains largely undisturbed by human activity, these features provide clearer evidence than in more developed or eroded regions. Meteorite studies connect Antarctica's geological record to cosmic history. The iron and stony meteorites found in ice fields reveal variations in composition that point to asteroids, planetary bodies, and early solar system conditions. Some meteorites are fragments of the Moon or Mars, offering direct insight into other worlds. The preservation of these rocks in Antarctic ice is unique, as the cold and dry environment prevents chemical alteration that would occur elsewhere. This cosmic connection links Earth's geology with the broader history of the solar system, demonstrating Antarctica's significance beyond our planet. The study of fossil flora and fauna underscores how climate and geology were interconnected. Ancient forests, wetlands, and river systems depended on tectonic configuration, soil formation, and temperature patterns. As Gondwana broke apart, Antarctica drifted south, altering climate, ocean currents, and ecosystems. Fossils document these changes, showing how continents, climate, and life evolved together. The ice preserves these links, allowing scientists to trace evolutionary and geological processes across deep time. Geological secrets in Antarctica continue to be uncovered through fieldwork, remote sensing, and subglacial exploration. Satellite imagery reveals rock exposures and sub-ice structures, while radar mapping detects mountains, valleys, and lakes hidden beneath ice. Drilling projects extract cores from bedrock and sediment, providing chemical and structural evidence of past environments. Together, these methods allow a detailed reconstruction of Antarctica's history, revealing a continent that has transformed dramatically over millions of years, yet remains a record of Earth's deep geological past. Antarctica's geological record is vast, spanning billions of years, from ancient cratons to relatively young volcanic deposits. It documents continental assembly and breakup, climate transitions, and the evolution of ecosystems. Ice sheets preserve fossils, rocks, and meteorites, creating a time capsule that continues to inform our understanding of the planet. Each new discovery adds to this record, showing that Antarctica is more than ice. It is a repository of Earth's history, connecting geological processes, climate, and life in ways that few other regions can match. Beneath the vast ice sheets of Antarctica, scientists continue to uncover mysteries that challenge understanding of life and Earth's processes. Subglacial lakes and water channels harbor microbial ecosystems that survive in complete darkness, extreme cold, and high pressure. These microbes are isolated from the surface, relying on chemical energy from minerals and ancient organic matter. Studying their DNA provides insight into how life can adapt to extreme environments, informing both biology and the search for life on other planets. Each discovery reveals complex networks of organisms that persist despite isolation, highlighting the resilience and diversity of life in extreme conditions. Climate modeling and ice sheet simulations are essential tools for predicting Antarctica's future. Using data from satellites, ice cores, and ocean measurements, Scientists construct detailed models of how ice flows, melts, and interacts with the atmosphere and oceans. These simulations help estimate sea level rise, the stability of glaciers, and the timing of potential ice shelf collapse. Models incorporate factors such as temperature trends, wind patterns, subglacial water flow, and ocean currents. By comparing predictions with observations, researchers refine their understanding of Antarctic dynamics, though uncertainty remains in projecting rapid or unexpected changes. Deep drilling projects provide a window into the continent's history. Scientists bore into ice and subglacial sediments to extract cores that contain trapped gases, minerals, and microscopic fossils. Ice cores reveal ancient, atmospheric composition, while sediment cores provide records of past climate, tectonic activity, and ecological shifts. Each layer is a page of Earth's history, preserved for hundreds of thousands or even millions of years. Studying these cores allows scientists to reconstruct cycles of glaciation, volcanic eruptions, and environmental change, providing context for current climate trends and offering benchmarks for validating models. Technological innovation is central to modern Antarctic research. Remote sensing uses satellites and radar to map hidden mountains, subglacial lakes, and ice thickness with remarkable precision. Autonomous vehicles, both underwater and surface-based, explore inaccessible areas, collecting chemical, physical, and biological data. Sensors embedded in ice or installed on glaciers track movement, temperature, and structural changes. Innovations in data collection and transmission allow continuous monitoring of a continent that is otherwise difficult to access, ensuring that research can proceed despite extreme isolation and environmental hazards. Despite these advances, many questions remain unanswered. The full extent of subglacial lakes, microbial diversity, and hidden ecosystems is still unknown. Ice sheet dynamics, particularly the response to sudden warming or melt events, are not fully predictable. The interactions between ice, ocean, and atmosphere contain feedbacks that are only beginning to be understood. Even with advanced technology, Antarctica retains areas that have never been directly observed, leaving gaps in knowledge about geology, ecology, and climate systems. These mysteries drive ongoing research, as every discovery leads to new questions and opportunities for scientific insight. Cutting-edge research continues to push the limits of understanding. Scientists combine field observations with laboratory experiments, computer modeling, and international collaboration to study processes that operate over scales, from microscopic microbes to continental ice flow. The integration of multiple disciplines, biology, geology, glaciology, and climate science, allows a comprehensive view of Antarctica as a connected system. Every expedition, drill, and remote survey contributes to a deeper understanding of how this frozen continent shapes the planet's environment, past, present, and future. Antarctica stands as a reminder of both the fragility and resilience of the Earth. Its vast ice sheets, jagged mountains, and hidden lakes evoke a sense of isolation unlike anywhere else on the planet. For humans, encountering this frozen world is both humbling and inspiring. The continent exists largely beyond our control, shaped by natural forces over millions of years. It challenges human imagination and curiosity, inviting reflection on our place in the natural order. To study Antarctica is to confront the scale of planetary processes and recognize the limits of our influence. Isolation in Antarctica is not just physical, it is also a measure of perspective. The distance from human civilization emphasizes how small and temporary human presence is compared with the continent's age and magnitude. Each research station is a fragile foothold, dependent on careful planning, international cooperation, and technology. Life here illustrates the balance required between curiosity and caution. Scientists live in a world that demands respect for natural limits, and their experiences show that knowledge often comes at the cost of patience and endurance. The fragility of Antarctica is evident in its sensitivity to environmental change. Ice shelves can collapse, glaciers can accelerate, and ecosystems can shift dramatically with small changes in temperature or chemistry. Human activities, even those far from the continent, can affect its ecosystems through climate change and pollution. Recognizing this fragility emphasizes the importance of protection. Treaties, regulations, and careful scientific practices exist not only to enable research, but to preserve a landscape that holds evidence of Earth's past and provides insight into its future. Antarctica also invites philosophical reflection. The continent is a mirror for human curiosity, showing the lengths to which we will go to explore, understand, and learn. Every ice core, rock sample, and microbial study expands knowledge far beyond its location. Discoveries here inform climate models, planetary science, and even the search for life on other worlds. By engaging with such a remote and extreme environment, humans confront both the limits of understanding and the power of observation. The continent becomes a stage for understanding planetary systems, as well as the human drive to seek answers in the unknown. Protecting Antarctica for future generations is essential. The continent's role in regulating global climate, storing fresh water, and sustaining unique ecosystems is unmatched. The knowledge gained from its ice, rocks, and waters has global implications, informing how we respond to climate change, ocean health, and environmental stewardship. Policies that minimize human impact, control pollution, and maintain the continent for peaceful scientific work are not merely local concerns. They are investments in global stability and planetary health. Antarctica reshapes our understanding of Earth by revealing connections that are otherwise invisible. Ice sheets store records of ancient climates. Subglacial lakes preserve ecosystems isolated for millennia, and ocean currents influenced by the continent affect weather patterns worldwide. Each scientific discovery reinforces the idea that Earth functions as a connected system, where distant regions interact through atmosphere, ocean, and ice. Understanding these links allows humans to see the planet as a whole, where changes in one place can ripple across continents and oceans. The synthesis of scientific discoveries in Antarctica highlights its relevance to humanity. Ice cores reveal cycles of warming and cooling. Sediment layers record tectonic and oceanic history, and microbial life demonstrates the boundaries of survival. Meteorites connect the continent to cosmic events, while observations of ice dynamics inform predictions for sea level and climate. Together, these insights form a comprehensive picture of how Earth operates, and they underscore the continent's significance as both a laboratory and a natural archive. Awe and caution coexist in human engagement with Antarctica. Its vastness, extremes, and hidden systems inspire wonder, yet its power and fragility demand respect. Scientific exploration requires patience, care, and humility. Each discovery brings new questions, reminding humanity that understanding is ongoing and certainty is rare. The lessons of Antarctica encourage careful observation, thoughtful action, and the acknowledgement of limits, both in scientific study and in broader interactions with the planet. Continued exploration is essential. Technologies like remote sensing, autonomous vehicles, and ice-penetrating radar allow deeper understanding without excessive human impact. Research in biology, climate science, geology, and oceanography continues to reveal the hidden complexity of the continent. By studying Antarctica responsibly, humans expand knowledge, improve global environmental understanding, and gain insight into the processes that sustain life on Earth. In reflecting on Antarctica, humanity is offered a vision of what it means to engage with a world larger and older than ourselves. The continent is a place of extremes, a record of Earth's history, and a test of human endurance and cooperation. It teaches respect for natural forces, the importance of protecting fragile environments, and the value of curiosity guided by evidence. By continuing to explore, study, and protect Antarctica, humans connect with a part of the planet that is both distant and profoundly relevant, reminding us that our actions are intertwined with the health of the Earth and the unfolding story of its future.